flight control switches. Pitch trim, reset, radios, set for departure. Okay, you're ready for start.
Number 3 clear. Four clear.
This is no ordinary C-141 cargo aircraft. It is NASA's Kuiper Airborne Observatory, which carries a 36-inch Cassegrain telescope to the stratosphere above most of our atmosphere and weather. Peering out a hole in the side of the aircraft, the telescope sees a universe that is invisible from the ground. Astronomers have good reason to fly with a telescope in the stratosphere. The light that we see is a mixture of many colors, here spread out into the visible spectrum. The electromagnetic spectrum ranges from high energy and short wavelength gamma rays, through X-rays, and ultraviolet radiation, to the light, the visible radiation we see. Beyond the visible part of the spectrum, lower energy, longer wavelength radiation, infrared and radio, bring messages to us of cooler objects, like clouds where stars and planets are born. When we look at cool objects in the infrared, like people or things in space, we see a whole new view. Our atmosphere blocks out most of the radiation from space. To see out, we send instruments up in balloons and rockets. We build astronomical satellites, and we fly through the stratosphere above almost all of the water in the atmosphere, on board NASA's Kuiper Airborne Observatory. Fortunately, at most infrared wavelengths, the Kuiper Airborne Observatory gives astronomers almost as good a vantage point as space. In 1983, the Infrared Astronomical Satellite, or IRAS, surveyed the infrared universe for 10 months. It made the first comprehensive maps of the infrared sky. Infrared observatories are able to see matter at low temperatures, like the planets and moons of our solar system, and the clouds of gas and dust that surround newly forming stars. Some infrared radiation reaches through the atmosphere to telescopes on mountaintops, but most infrared energy travels billions of miles through space to be absorbed by water in the Earth's atmosphere less than 10 miles above the ground-based observatories. Infrared astronomy from aircraft was first conceived in the 1960s by Dr. Michael Bader of the Ames Research Center in California and by Dr. Gerard Kuiper, an astronomer at the University of Arizona. One of the problems that Kuiper investigated was how our solar system formed out of a clump of interstellar gas and dust. His research is carried forward in the observatory that bears his name. For the Kuiper Airborne Observatory is often used to study stellar nurseries, places where stars and most likely planets are formed. The Great Nebula in Orion is one of the closest star-forming regions, only 1,500 light-years away. Here we have an intimate view of star birth.
Orion is one of the most familiar constellations in the sky in the late autumn and the winter. Most people can identify it. Orion the Hunter. A prominent feature is the belt, and hanging down from the belt is Orion's sword. And down near the end of the sword, there's a glowing cloud.
What makes this hot cloud of gas and dust glow are the newborn stars within it.
We learned how to run this instrument looking at tough things like the galactic center. Now at last we're getting to look at something that's supposed to be easy, namely Orion.
Tonight, we will observe the Great Nebula in Orion from the Kuiper in an effort to learn more about the process of star formation. First, however, the aircraft and the telescope on board must be prepared for flight. It all starts in the early morning on a particular flight day. The ground crew will roll the airplane out at 6:30. and roll it across the ramp for fueling. And by the time most people get into work, the airplane is back in the hangar and fully fueled. The computer people may spend all day pre-flighting their equipment. The telescope is rigorously pre-flighted. Members of the observatory crew are getting ready for tonight's flight. These consoles of instruments and the lack of windows make the Kuiper look from the inside more like a high-tech ship than an aircraft. So, like a ship sailing the stratosphere, the Kuiper navigates by the stars. The position of the celestial object that is being observed determines the course of this flying observatory.
The important objects here are the T-Tau, IC 443, and Orion.
Right.
And of course, Jupiter has to stay at that length.
The telescope is inside this chamber. 36 inches, or 9/10 of a meter in diameter, it looks out through an opening on the left side of the aircraft. The flight path of the Kuiper Airborne Observatory enables astronomers to keep the telescope fixed on the objects they're observing. And the telescope's unique design enables it to stay on target. To counteract the vibrations and motions of the aircraft, this telescope is guided by gyroscopes and balanced on a bearing which floats on a cushion of compressed air. It tracks its target even when turbulence bounces the aircraft around. The telescope is often used by students who are members of research teams.
A great advantage of airborne astronomy in the space age is that it provides an opportunity to train students. Gives an opportunity for students to build apparatus, to fly it, and do frontline research, all in the period of a graduate student's career. One of the students who's worked with me is Jacqueline Davidson, now Dr. Davidson, who is an astrophysicist at the Ames Research Lab.
Major astronomical discoveries have been made from the Kuiper Airborne Observatory. In 1977, Cornell astronomer James Elliott and his student Ted Dunham were flying across the southern Indian Ocean. They were chasing an occultation of a star by the planet Uranus. When a planet moves between Earth and a distant star, the planet blocks the light from the star. This is an occultation. To see the occultation, Elliott and Dunham traveled to Australia and flew the Kuiper out over the ocean to catch the shadow of Uranus. The Kuiper was able to be at the right place at the right time, within the moving shadow of the planet.
So it's a big challenge to understand the positions and the motions well enough to know where this shadow is going to be. And that's where the Kuiper Airborne Observatory comes in, because many times these shadows don't cross over telescopes that are on the ground. And if they do, it may be cloudy that time and you would not be able to observe the occultation. So the Airborne Observatory has been a big boon to our work.
When the Kuiper flew on its mission to observe Uranus, Ted Dunham, who was then James Elliott's graduate student, was on board gathering data for his doctoral thesis.
And I remember we were distracted by something. I glanced back at the chart, and something had messed up.
Maybe there was a very high cloud that had just passed in front of the telescope.
Pete Kuhn was flying in the back. He was a meteorologist, and he had an interest in clear air turbulence, but he also was running these radiometers to measure the water vapor, and he told us there was only 10 microns of water over us, so we couldn't possibly have had any clouds. And while we were arguing about whether it was an equipment problem or whether it was real or whether it was a telescope problem, another thing happened. It was much shorter than the first one.
I think about the third time it happened, I mean, there was really no other explanation than it was probably something real, i.e. occultation by something near Uranus, maybe a small satellite.
We finally saw the occultation by the planet, and then that was a key piece of my thesis data, so I was pleased to see that it actually happened. And there were loud cheers and carrying on. And then the star came out the other side of the planet, and we saw the light regain its original level. And then we just sat to watch.
Then Dr. Elliott said, how much farther can we go here just to make sure, see if these things repeat at the same distance? This was a sweaty palm situation because we were then something like 2,000 or more kilometers from Perth, Australia. There was a tropical cyclone moving down the west coast of Australia south of Carnarvon. So we were eager to get that airplane turned around and get back. But it seemed like there was a pervasive science reason for continuing on, so for another 30 minutes we did.
And sure enough, the similar kinds of dips happened on the way out that happened on the way in. And it looked like we had seen a belt of satellites around the planet. And it wasn't until maybe 3 days later when Jim had the chart at home, and he and his wife unfolded it on the living room floor and folded it over on itself, that they realized that 4 out of these 5 dips were just smack on top of each other, and the 5th one is offset a little bit. And that one turned out to be the Epsilon ring, which is elliptical, and the others are much closer to being circular. And that's, I guess at that point is when you'd have to say that the rings were discovered.
Planets are not the only objects in our solar system that are observed from the Kuiper. The moons of planets, asteroids, and comets are also studied. Comets are remnants of the stuff that formed our solar system. In 1986, when Comet Halley returned from its outer orbit to the Earth's vicinity, astronomers used the Kuiper Airborne Observatory to take a close-up look. Astronomer Umberto Campins wanted to know what the dust on a comet is made of.
The dust in Comet Halley had a large component of organic solids. And by organic solids, I mean solid material that is made up of organic molecules, long carbon chains with hydrogen, nitrogen, and other elements that are the raw material that is needed for life, but not life itself.
Through us, life on Earth has the amazing ability to understand our kinship with the universe. Think about the difference in scale between the Earth and our solar system. And then, between our solar system and the arm of our galaxy where the sun shines among other stars. And then the size of our galaxy itself, which is one of a cluster of local galaxies. The magnitude of the universe is awesome. Yet astronomers are able to analyze the electromagnetic radiation from distant objects, even ones that are billions of light years away, so that we can tell what those objects are made of. The key to interpreting the electromagnetic messages we receive is in these lines, called the spectra. This is what electromagnetic radiation looks like when it's seen through a spectroscope. These spectral lines are like fingerprints. They identify the atoms and molecules that an object in space is made of. By carefully measuring and analyzing spectra, astronomers learn about the size, temperature, mass, composition, and motion of comets, planets, stars, clouds of dust and gas, and distant galaxies.
This is my favorite right there.
I like that, yeah.
That's HCN.
Is it? I think you're right.
Yep.
Just gonna measure them off here.
The spectral fingerprints of Comet Halley revealed the presence of ice, frozen water, along with methane, ammonia, and other gases. Earthbound astronomers had not identified water in comets because the water in our atmosphere clouded the data. But on the Kuiper Airborne Observatory, Dr. Harold Larson of the University of Arizona was able to prove what had been suspected. He found the water in the spectra of Comet Halley, which confirmed that comets are essentially dirty snowballs hurtling through space. This discovery helps us understand part of the mystery of life.
If Comet Halley is rich in organic material, that indicates that most comets probably are. And we know that the Earth has had many collisions with comets, and that very possibly a lot of the water on the Earth came from collisions with comets. Because comets are so rich in water ice, they possibly contributed to the Earth's oceans. And if they contributed the water, they might have also contributed a considerable amount of these organic molecules that came in the form of solids originally and mixed in with that primordial soup that was the oceans of the early Earth. And therefore, they would have made the evolution of life on Earth much easier than if there had been no organic material.
Organic material is made of complex molecules, which are made of simpler elements: carbon, nitrogen, oxygen, and more. And these elements are formed in the hearts of stars.
When the universe was formed, only hydrogen and helium was believed to exist. And so the rest of the elements which make up our bodies and the Earth and our atmosphere came from the interiors of stars. And it's the observations of the supernova 1987A which confirmed for the first time what exactly goes on in the interiors of stars. We have had successful theories for many years, but supernova 1987A was the first chance we had to really look all the way through a supernova and to explore throughout its infrared spectrum all the different elements which were ejected into the space around it.
A supernova is an extraordinary cosmic event, the explosive death of a massive star. It releases enough light to outshine an entire galaxy. Supernovae that explode within or near our galaxy may be visible with the naked eye, but most are not seen. Interstellar clouds of dust in the plane of our galaxy block them from view. In 1054 AD, Chinese and American Indian observers recorded a supernova. Today, the remains of that explosion continues to expand in space. In the late 15th and early 16th centuries, 2 more supernovae blasted into view. These were just before Galileo began to observe celestial objects with a telescope. When supernova 1987A exploded 4 centuries later, astronomers got their first close-up view of the death of a star.
Some people might wonder why, if there are so many stars in our galaxy, why only one every 400 years explodes to be a visible supernova. Well, most stars live very quiet lives and die by just sort of fading away. But in the elementary astronomy classes, we like to say only the most massive stars live vivacious lives and die dramatic deaths.
When an old star dies, in many cases it will die some kind of a violent death in which it throws off a lot of material. That material, much of it, or some of it, turns into dust. The dust is part of new clouds, and then those clouds collapse, and it's the material out of which you make a new star. It's the material out of which you make everything on a planet. So we're the dust of some old star.
The stuff of which stars are made of is abundant at the center of our galaxy, shrouding it from view. But the infrared radiation, the heat, from the core of the Milky Way penetrates these clouds of dust and gas, allowing astronomers to observe what is happening there.
One of the most exciting places in our galaxy must be its center. There is so much we don't know about that region of the galaxy that it's exciting. Every observation we make is an exciting new discovery. And for so long it's been a mystery because it is enshrouded in dust. And so you have never been able to make an optical measurement of the center. And only in the 1970s, were we able to start looking into this region in the infrared and discovered that there was a huge amount of energy coming out from the center.
This luminous area at the center of our galaxy seems to be the birthplace of millions of new stars. However, studies of motions of stars in the region show the gravitational pull of a mass far greater than that exerted by stars and other observable objects. Things act as if within 1 or 2 light years of the center, there is something with a mass of between 3 and 4 million suns. Some astronomers maintain that this massive yet undetectable object is a black hole, a stellar graveyard beside a stellar nursery.
For a number of years, astronomers have suspected that the centers of some galaxies may contain very massive black holes, which consume large amounts of interstellar material, and in the process become very powerful radio and infrared sources, emitting many times the luminosities of the rest of the galaxy combined. Another thing which is evolved out of observations done with Kuiper Airborne Observatory, among other astronomy facilities, is that they're very often the site of very intense bursts of star formation, very much like the kinds of activity that you see in nebulae in our galaxy, like the Orion Nebula or M17 or M8, but on a much more massive scale. The things that we look for in our studies of galaxies with the Kuiper Airborne Observatory are to try and understand how these systems evolve. At one time, galaxies were just big clumps of gas, and under the action of gravity, they condensed to form stars in either spheroidal distributions or, in the case of spirals, in large disc-shaped distributions with the spiral arms. One of the things we try to understand is how these processes occur, both initially and then as a galaxy evolves in time.
On tonight's flight, astronomers will map the closest star-forming region, the Great Nebula in Orion, to detect the faint infrared radiation that has traveled across our galaxy from the nebula. The telescope and the detectors must be very cold. Otherwise, the infrared radiation from space would be lost in the heat of the instruments. Part of flight preparation is pre-cooling the telescope to about -20 degrees centigrade prior to takeoff. This is done using a giant specialized refrigeration system and liquid nitrogen. The detectors, which will collect the faint infrared radiation, are pre-cooled to a much lower temperature. The infrared detectors are mounted in the center of a tightly sealed cylinder called a dewar, a giant double-walled thermos bottle. Filling the dewar with liquid helium lowers the detector temperature to around 4 degrees Kelvin. That's -269 degrees Celsius. At the core of the dewar, helium-3, an isotope of helium, further chills the detectors to 0.4 of a degree above absolute zero. Astronomers use special instruments to analyze the radiation that comes through the telescope. One of the techniques that have been developed for observations from the Kuiper is polarimetry. Designed to study the orientation of light waves, this polarimeter will be used tonight to observe the Great Nebula in Orion.
Most people's familiarity with polarization just has to do with Polaroid glasses. If you have Polaroid glasses and you go fishing and there's a glare from the water, the Polaroid glasses will cut out the glare. But now if you take the glasses off and turn them at 90 degrees, it doesn't cut out the glare, as the light has a certain property that depends on an orientation in space. Now our instrument has a characteristic that we can tell in what direction it's polarized.
What do you think? I'm excited. Oh, I am too. That's great. What do your kids think about all this?
Two teachers, Sandra Engel and Maggie Gwaltney, will join the astronomers on tonight's flight and experience discovery firsthand as a part of the research team.
W3. Most of the clouds don't have nice names like Orion. They have names that sound like license plate numbers. And the signals from all those 64 detectors come out and go into that box there. And that's a thing called a digital signal processor that turns the signals from the detectors into numbers, and we can store in a computer. Now this is the control rack. We run the apparatus from this, and then I'll have another student, Jesse Dotson, who will sit over there, and 5 minutes after we've taken the data, she'll show us a picture of some sort that tells what we've just done.
These teachers are participants in NASA's Flight Opportunities for Science Teacher Enrichment, the Foster Project, which is designed to educate teachers about all aspects of airborne astronomy, and through them, reach out to students and communities across the nation. Both of the teachers flying on the Kuiper tonight teach at schools in the nearby San Jose Unified School District. In addition to the pilot, co-pilot, and flight engineer, the Kuiper has a highly trained crew in the main cabin whose work is coordinated by the mission director. These crew members operate the telescope, track the stars and other objects that are being observed, and maintain the onboard computer system. Teamwork between the observatory crew, the astronomers, and the pilots on the flight deck is the key to the Kuiper's success. Now, the Kuiper is flying so that the telescope is pointed at the Great Nebula in Orion. At the telescope tracker's workstation, the nebula appears on the screen, and the crosshair shows that the telescope is on target. Tonight's data will be analyzed for months to come. But the astronomers already know that they have made the first comprehensive map of the nebula with polarimetry. These observations are another contribution to the totality of knowledge about the universe, one more piece of a truly cosmic puzzle. But what airborne astronomy offers is more than the information that can be gleaned from a platform in the stratosphere. In the future, NASA will fly the next generation Stratospheric Observatory for Infrared Astronomy, SOFIA, with an even larger telescope. Until then, the Kuiper Airborne Observatory is the place where new technology is tried out and perfected. It is a training ground for the astronomers of the future. It is a place where teachers participate in the process of astronomical discovery. And it is a window into astronomy itself for those who want to learn about the mysterious infrared universe through which our Earth, a spinning sphere, revolves.